In this video, what we're going to do is we are going to go from the name of a compound to the formula of a compound. Now, in our videos and lectures and readings on going from the formula to the name, we know that the cation name goes first. So that means that the symbol for the cation also goes first. So we know from the periodic table that the symbol for magnesium, okay, for the word magnesium is Mg. We know that the symbol for chloride, well, there is no chloride on the periodic table. Now, is there? But we also know that chloride looks like chlorine, which is an element on the periodic table, because this chlor is a root of the word chlorine. Okay? Because this is a binary compound. It's magnesium and chlorine. The I just indicates that it's the anion, that it came second. So we have chlorine. Now, this alone is not enough to tell us the formula because it doesn't tell us the ratio of magnesium to chlorine. In order to do that, we need to know what the charges are. Okay? So we know that since magnesium is an alkaline earth metal, since it's in the second column of the periodic table, so far, we may not know the reason yet, but we know that magnesium has a 2+ charge. And we know that chlorine has a 1- charge. So we have this plus 2+ charge, and we have a -1 charge. And they have to somehow add together, pardon me, they have to add together to equal 0 in an ionic compound. So that must mean I have, in order for them to balance out and cancel each other out, I must have 2 chlorines. So my formula for magnesium chloride must be Mg Cl2. Okay. Now let's go to our next example here, which is tin 4-sulfide. Now note we have a Roman numeral here. Tin 4 is a type 2 metal. That means that tin can have multiple possible charges. So tin, which is Sn, can have multiple possible charges, but the Roman numeral 4 tells us that it's 4+, so I don't have to look it up. Now, when I look at the second part of the name, the sulfide, the SULF, the sulf, tells me that it's the element sulfur, or it comes from the element sulfur. It's the ide, so it does have to do with sulfur. And since it does end in ide, it's the anion form of sulfur, which, based on what I know about the periodic table so far, I know that it is 2-. And just like our previous example, I have a +4 charge, so 4+, and it needs to add to sulfur's 2+, I'm sorry, that's the wrong color, or it needs to add to sulfur's 2-, I'm sorry, to equal 0. But that doesn't work out that way. So it looks like what I need to do is have 2 of those. So I must have 2 sulfurs. So my final formula must be Sn S2. And I realized one thing I did that may be confusing now that we've talked about polyatomic ions is I put this in parentheses. The only reason I put it in parentheses was to help set it off as an anion. You don't have to include the parentheses in the formula unless the anion contains more than one element. So I'm sorry, I didn't mean to. I just realized that probably may have added some confusion. Okay. So our last couple of examples here. Okay. Here we have another example of a ionic compound. I know it's ionic because it contains cobalt, which is a type 2 metal. Cobalt, according to the periodic table, has the symbol CO, and the Roman numeral tells me it's 3+. But then I come to this nitrate. It doesn't end in "ide," so I know it's not an anion of an element. Sorry. I'm using a new document camera, so it keeps thinking things are out of focus. It doesn't end in "ide," so it doesn't come directly from an element. It ends in "ate," which is a dead giveaway that it's a polyatomic ion. Okay? So I'm going to look at my chart, I'm going to Google it, I'm going to look in my flashcards, whatever, my memory, hopefully, that's what we're really hoping here, to figure out what nitrate is. Well, nitrate is NO3-. Okay? The fact that it's NO3- means that the whole thing has a -1 charge. So I treat this in a similar way to an element in an ionic compound that has a -1 charge. So cobalt, in this case, it would be 3+ plus a -1 charge to equal 0. So how many -1 charges would it take to equal 0? Well, in this case, it looks like since I'm starting with 3 positive charges, it will take 3 negative charges. Or in this case, 3 nitrates. What this means is that I will have 1 cobalt and 3 nitrates. So cobalt, but, and this is key, I have 3 nitrates, 3 whole things. I said I made a mistake on I could have confused you on the last one. Since I have 3 nitrates, I have 3 NO3s. So I put NO3 in parentheses and then put 3 right after it to show that I have 3 of those things inside. That's how we go from the name to the formula. Now, the very last type we're going to talk about is the type 3. This is naming binary non-metal compounds. Very straightforward. You'll notice that I didn't put them in blue or red because I'm using blue to represent cations and I'm using red to represent anions, and the anion-cation nature of these compounds is a little weird, and we're not going to talk about it. Not because you can't handle it, but just because I don't want to get into it. But we do have our prefixes, di and pent. These are things you just have to memorize. Remember, di means 2, pent means 5. So I have 2 of whatever comes after it. So in this case, I have 2 nitrogens, which is N. I have 5 oxygen, 5 oxides, which is oxygen. So I have N2O5. And that is how you name type 3, or how you generate the formula for type 3 compounds. So that is our general quick review on how to go from the name of a compound to the formula of a compound, which is very useful considering the fact that most products only contain the name of a compound and not the formula of a compound, as useless as that may be.